In this video you will learn what a voltage divider circuit is and according to which rules the voltages are divided or spread across several electric components in a circuit. You will learn here that there are basically two variants of the voltage divider and that you have to decide which variant to use depending on the given and also the sought for values of the respective problem you are trying to solve. And by the end of this video you will be able to calculate missing voltages in your circuits quickly and easily. And as always, there's going to be a summary of the most important facts from this video at the end for you. And my name is Andreas from The Fearless Engineer, and here we go. Now, before we dive into this concept of a voltage divider and the voltage divider rule, let's quickly look at this definition here taken from Wikipedia. It says there that in electronics, a voltage divider is a passive linear circuit which produces an output voltage that is a fraction of its input voltage. And voltage division is the result of the distribution of input voltage among components of the divider. So without going into too many details yet, we can glimpse from this definition that the voltage divider is about finding the fraction of distribution of voltages across a circuit. So in which ratio, in which relation does a total voltage split across the components in a circuit. And in order to dive deeper into the meaning behind this rule, let's quickly recap two items taken from previous videos, which we need in order to understand what's going on with the voltage divider. The first is Kirchhoff's second rule, which states that the partial voltages across the resistors in a loop sum up to the total voltage of the source. That's the famous loop rule. And if you have seen the video which I made about the loop rule, you also know the equation behind this loop rule here. And the second is the current through resistors which are connected in series is identical. So if you place several resistors behind each other in an unbranched network, they're going to share the same current flow. And based on these two observations, we can go into the details behind the voltage divider. Let's take a look at this first circuit here. You can see a voltage source on the left, which has a voltage of 5 volts. And then you have two resistors in an unbranched network, the first with 100 ohms and the second with 200 ohms. And in between the resistors, above, in between, and at the bottom, the simulation has placed the electric potential. So at the topmost point, we have the full 5 volts provided by the power source. And at the bottom, we have 0 volts. So on the way from positive to negative terminal through the circuit, the current or the charges in the current have shed their entire electric potential. It has dropped from 5 volts to 0 volts. And it has been distributed among the two components in their path. So if you compute the difference between the potential atop the first resistor and at the bottom, you arrive at a voltage drop of 1.67 volts. And at the bottom, the second one here has a voltage drop of 3.33 volts. And if you look closely at these two numbers, obviously you will note that the lower one is double the upper one. So if you look at the resistance values again, you can also see that the lower one is double the upper one. So there seems to be a direct relationship between the size, the magnitude of the resistance value, and the voltage drop in a series connection. And this is what we're going to investigate further now in the upcoming slides. Now let's take a look at the first variant of the voltage divider. This video is about the voltage divider in a nutshell, which means we will not go into a lengthy derivation. We will look at the formula which you can directly apply to a circuit of your choosing. And the first thing is to always look at what's given to us. And in this example here, we have the same circuit diagram as we have looked at on the previous slide. We have the voltage source, we have a resistor 1 and resistor 2. We have two voltages dropping across the resistors, and we are given the second voltage drop. We have both resistance values, and we are looking for the voltage drop across the first resistor. And we are not given the total voltage of the source in this example. And for this first variant, you can apply this rule here, which you can see on the left side. So the voltage drop across the first component is the product of voltage drop across the second component, which is given, multiplied with the ratio of the two resistance values, R1 divided by R2. You can apply this formula directly, insert the values which might be given to you in an example exercise, and then you can compute the voltage drop across U1 based on this very simple equation. Now in the second variant, we still have the same circuit here, but with a major difference, because now we do not have the voltage drop across the second component here. U2 is not given to us, but we now have the total voltage provided by the source. And for this variant of the circuit, we can apply this equation here. So the voltage drop across the first resistor, which we are looking for, is the product of total voltage drop multiplied with the ratio of resistor number 1 and the sum of both resistors, R1 plus R2. So in situations such as this one here, where you have the total voltage given, you can apply this formula here instead of the previous one. And now let's take a look at examples of both intentional and unintentional voltage dividers. Now, firstly, let's talk about something where we want to construct a voltage divider. Let's imagine a situation where we want to power an LED with a sufficient amount of voltage, but where we want to limit the current flow through the LED by carefully controlling the voltage in a way that within the nonlinear characteristic curve of the LED, we do not exceed a certain safety threshold. And in order to do this, we can construct a voltage divider which secures the LED, and also we might want to place a resistor in series to the LED. And if we connect this two-component network to our voltage divider, we can carefully limit the amount of current flow through this small sub-branch by carefully choosing the degree of the voltage division. This example is also a good example for something called the loaded voltage divider, because if we connect something in parallel to an existing voltage divider, we change this distribution ratio, but this is something for an upcoming video on the loaded voltage divider. But in practice, this is one of many applications where a voltage divider is used. The second one is an unintentional voltage divider. Take a look at this setup here. You have a wall socket which powers your power drill here on the right, and because you want to drill a hole into a wall which is very far away from the wall socket, you are using such a cable drum here, and which you place in between the wall socket and the drill. And due to the length of the cable, this cable drum behaves like a resistor of its own, and depending on the length of the cable and also the quality of the cable, this will be either small or large, but in any case, it's going to be a second resistor in this unbranched network here. And this is why the cable drum with R1 and the drill with R2 are going to act basically as a voltage divider, which means that depending on the size of the resistance value of this cable drum, the full voltage from the wall socket will not be available for the power drill, which takes away some of its power, so to speak. And this is a good example for an unintentional voltage divider. Well, let's quickly summarize the major points here from this video. The first one is the voltage divider rule can be used to compute the ratio of division of voltages in a circuit where the components are connected in a series connection, in a series manner. Secondly, depending on the quantities which are given and which you are looking for, it's necessary to use the appropriate version of the voltage divider. In the respective case, we have looked at two versions here, and you have to decide which one to use. And one indicator is, do you have the overall voltage given, or do you only have a partial voltage given? And this is the point for which you have to look in order to choose the correct variant. Then thirdly, the derivation of the voltage divider rules, both we have looked at, can be achieved with the help of the concept of current equality and also with Ohm's law. And this is something we're going to look at in the next module, where we will derive the voltage divider equations, which we have looked at in this nutshell video here in a very short manner. And also thing you might want to take care of or pay attention to, the rules which are shown here, they only apply if the current through the components under consideration is equal. So one of the most important facts about the standard voltage divider is that the current through the first resistor must be identical to the current through the second resistor. If this is not the case, then you cannot apply these formulas here. And in case you have something like the setup which I talked about on the previous slide with the LED and the resistor which we place in parallel to one of the voltage divider resistors, we take away some of the current flow, and in this case we have a so-called loaded voltage divider, which we will also look at in one of the upcoming videos. This is all for now. I hope you enjoyed the video. If you have any questions, drop me a comment in the comment section down below. And as always, have a nice day. See you next time here on The Fearless Engineer.